Okay, so hello everyone, and welcome to the TechUPGRADE podcast series, the official series of the European funded TechUPGRADE project. In this series, we will take you behind the scenes of the project, sharing perspectives from our partners, discussing the ongoing work, and highlighting the most interesting things and the people who are contributing to Europe's innovation landscape in the field of energy. Before we begin, do not forget to follow our social media pages on LinkedIn, Instagram, and Facebook, and also subscribe to our channels on our YouTube and our Spotify channel. You will find all the relevant links in the episode description below. Today, I am delighted to host Professor Peter Weinberger from TU Wien, who is also the leader of work package 3 in the TechUPGRADE project. So in this episode, we will explore the chemistry side of the TechUPGRADE project, its scientific foundations, and the exciting work that is being carried out in the work package. Professor Weinberger, welcome to the podcast. It is great to have you here with us. The first thing with which I want to begin is to introduce yourself, to tell us a little bit about your work in TU Wien, and also what are you doing in the TechUPGRADE project?
It's a great pleasure to be here and welcome also from my side. My name is Peter Weinberger. I'm a trained inorganic chemist. I'm a professor in the research group of magneto and thermochemistry at the Institute of Applied Synthetic Chemistry at TU Wien here in Vienna in Austria. And we are dealing more or less since 15 years with the topic of thermochemical energy storage, and especially the side of developing new materials. And that is the reason why the coordinator of this project was asking us to join this wonderful interdisciplinary consortium to introduce our expertise in these materials.
Okay. I know that your team is working on reactive materials, so that these materials are making the technology possible. Can you explain us what is the reactive materials and what actually these materials do?
The basis for this is actually a reversible reaction between a solid and a gas to form another solid. And this must be 100% reversible, because otherwise it wouldn't make any economic sense. The idea behind this is that we can use rather cheap and abundant gases like water vapor to make this reaction. The materials which can do that are, for instance, salts, which can uptake water molecules into a hydrated form. And with this reaction, we are releasing heat. And this is exactly the same heat you will need to get rid of the water vapor out of the salt again. So this reversibility, input of heat and output of heat, and cycling the material, in principle endless, is the basis for this technique.
Okay. So can you describe us in simple terms? How is the process of identifying these materials? How this process works?
Well, in principle, you can start from the scratch with some basic chemical knowledge, and the oldest technology known to human is actually the limestone calcination, which was done already in the antiques. And when you then pour water on that, it becomes hot again and releases the same heat as you needed to calcine the limestone. This observation, after decades of development, finally brought the idea, okay, we cannot do that only with something like limestone, but we can do that with other materials, salt materials. And our research group started with an algorithmic search, database search, when physicochemical dehydration and rehydration enthalpies, these are the energies to put in and out, are known from earlier work, and put them together in an overview. What are feasible, possible new reactions? And usually you start with simple systems. And to give you an idea and a flavor of what I mean, I have brought some models. A typical salt looks actually like that. That's sodium chloride. Everybody knows it from salting your soup. You have an alternate orientation of the sodium and the chloride in all three directions. That's the most primitive possible orientation. We, in our project, use a different compound. It's strontium bromide. And the ratio between the strontium and the bromide is not 1:1, but it's 1:2. So imagine the same system now omitting every second red position. That would be the strontium, and the white ones would be the bromine. So you get a different system that distorts the whole thing. So the distances here are not the same anymore, but in a different ratio. Nevertheless, the principle is the same. And each of these units has space to get water molecules in between and widens finally. So there is a small volume work, but more important, new bonds are formed. And when these bonds are formed, then we release energy. And if we now put heat into the system, we break these bonds again, and the water comes out. So they can back and forth charge and discharge this salt. This is a very simple idea. The problem is always in the details. Because you can imagine that this works only when the water molecule, which has a non-zero volume, it has a size, when it has to penetrate this lattice. So if that is too small and too dense, then it cannot get in. But I mentioned already, in our case with strontium bromide, only every second of the red positions is filled. So there's empty space. So that's why such salts can be used to enter the water molecules in the voids and build these new bonds. And of course, these are simple salts, but as a chemist, you always want some new limits, new boundaries. And that's what actually our synthetic chemistry approach is, and is part of this project, that we are also looking for alternative solutions, not the well-known strontium bromide, and look for more fancy stuff in the hope that it can at least perform as good as the known one, or at best being better.
Okay, and this whole process about the difficulties that you mentioned was something that you encountered in TechUPGRADE, or was something new to you and you encountered it through your experiments, or it was something that you find and it was, a surprising outcome of experiments?
Not really. Actually, since 15 years, we are working on this topic, and it's usually every new compound you are starting to work with is a surprise. Because never ever nature is doing everything so straightforward. Yeah. Uh, there are subtle differences between the compounds, size changes, bond angles, distortions. So something which you are not foreseeing, and just when you are doing it, realizing, okay, here is a problem. And with time, of course, you can derive some building principles, some general ideas, what is more likely to work and what is less likely to work. However, never think something won't work because the first trial doesn't work. This is a very important message. But of course, if you have a time pressure, then you are not playing around with the not so successful experiments, but optimize the successful. In our case, we have been looking for alternative salts based on a mixture of cations. These are positive charged, let's say the red ones, and the sulfate, which is actually an SO4 anion, which would be the white ones. To give you an imagination, if you have an SO4, you might have already in mind a geometry. And in fact, this is the geometry. The sulfur sits in the middle, and on the corners of this tetrahedron, you have the oxygen. And this SO4 tetrahedra are now instead of these white balls. And on the red positions, here we have now our positive charged cations, and they can be surrounded by 6 water molecules sitting on the corners of an octahedron. And now try to densely pack this combination. It's not easy. You need space. On the first glance, you would think that won't work. Oh, it works. The good thing is you have now a lot of flexibility. A lot of flexibility means that the water molecules can more easily penetrate the structures from all sides, and the reaction works even better than with such a simple system like this.
So you ended up with a family of materials called Tutton salts. And can you tell us a little bit more why these are better competitors than other materials?
In fact, it's more the complexity of these materials, why they are better. Because if you imagine you have, let's say, billiard balls on a table, very dense, touching each other, then of course you have voids. You can put a second layer of billiard balls now in these voids on top, but still there are voids. If you now put, for instance, some different sized balls, then you cannot do that so easy. It's a little bit more a mess. You don't have this very exact same size of this material. So there are additional channels where the water molecules can diffuse. So in fact, not being perfect in the sense of same size is an add-on in flexibility. And this is only possible if you have a class of compounds which allows for this flexibility. And not all salts can do that.
You mentioned flexibility. Know, let's say, know from several discussions that these materials need also to be stable in different heating and cooling cycles. Why is that?
That is an extremely important prerequisite. I mean, from the economic point of view of application, we of course don't want to change the filling of these reactors every 3 cycles because the material is gone. So it will only pay off if this is a more or less once forever filling, and then you can go for thousands of cycles. So that of course means two different aspects of stability. First, the molecular scale. There shouldn't be any deterioration on the molecular scale, so a kind of destruction of the ingredients of this material. And the second thing is, of course, these are forming crystalline, microcrystalline powders. And of course, upon this reaction with the water vapor, they agglomerate, and maybe there could be, in worst case, a kind of sintering of gluing together of small particles into bigger particles. And that would be not in favor of a good cycle stability, because the smaller the particle, the better the surface to volume ratio is. And if you have a gas solid reaction, we want a lot of surface and only a small volume, because otherwise it takes so long to penetrate into the inner part of this particle. So these two things, molecular stability and particle stability, is a crucial prerequisite for a good working material.
Okay. And in the project, how many cycles these materials went, and do you have any results of these cycles?
There are, of course, not endless time in any project, so you have to uh, work in a stepwise process. Of course, the first thing was when we made up all these new combinations of Tutton salts, that we, of course, measured only very small quantities in the milligram scale in our simultaneous thermal analysis equipment. There you make, let's say, 10 cycles and have a look whether the energy input and output stays stable. If you see already a decrease after 10 cycles, there is no need to look further, because then it won't be stable. If, on the other hand side, you see almost no change, or no change within error margins, I would say, in this measurement, then you run for bigger sizes. And this our partners actually are doing. And so far, we did, with the best compounds we found, several hundred cycles without seeing any deterioration. And neither on the energy input output nor on the particle behavior.
Great. You mentioned the partners. How is your work connected with the engineers? What experiments have you run so far, and what the result of the technology, if it is successful, means for the future of the project?
Wow, that's a lot of questions.
Yeah.
So let's start with the partners. First of all, the engineers, which are really outstanding to my personal opinion, they design a reactor, they make the reactor. We help them in filling the reactor. We started with a test rig of something like 100 to several hundred grams. These are the partners at the university in Twente, uh, and run some cycles there and look how the material behaves. The second very important engineering partner is, of course, the DLR in Germany, now in Cologne. They have been in Stuttgart before. And they have already prepared a 5 kilowatt reactor. And in the end of the project, we envision to have even a 35 kilowatt reactor. And this only works, of course, you don't start just screwing something together, with a lot of theory, which I personally, as a chemist, don't understand very much, but I'm fascinated how they design it. And there's a lot of design from DTU in Denmark, our coordinator, Ahmed Arab Koshur, and his team. And we have engineers who are, in fact, manufacturing these reactors. This is TMEC in Ukraine. Uh, for me, it's masterpieces they are putting together. It's fascinating how these things work. And in the end, we are envisioning that we are able to use these reactors with up to 50, 60 kilograms of our material and run several cycles just to make sure that this system works under realistic conditions.
Great. And as we are approaching to the end of our discussion, if you want a listener of ours to have a quick to get a quick message about the materials in the TechUPGRADE project, what would you say to him or her?
Mhm. First of all, it's an integral part to have a very in-depth understanding of the chemistry of these materials. It's usually not easy for a special application with a desired user case. Let's say you have a waste heat you want to use to charge your materials from an industry or from solar heat or whatever. Then you have to find the proper material which working window is exactly in that temperature range. And this is only possible if you have an in-depth chemistry knowledge about these dehydration and rehydration steps. And if you are lucky, and I have to say that it's not so straightforward to design things only from your mind. Sometimes you need also some luck. Yeah? And in our case, it was a mixture of knowing good chemistry and having some luck to get this new family of Tutton salts. And with that, we are now having a material in hand which can be, due to its diverse composition and complexity, tuned, fine tuned into certain application windows. And that is hopefully one thing which can allow a breakthrough on commercial economic scale for this technique.
Great. Thank you so much. This brings us to the end of our second episode of the Tech Upgrade series podcasts. We would like to thank you very much, Professor Weinberg, for sharing all these insights with us and with our audience, of course. So, if you enjoyed this podcast, please follow our social media pages and subscribe to our channels on Spotify and on YouTube. We will provide all the links in the description, and please stay tuned for the next episode uh, of our series. So until then, take care and see you soon. Thank you.
Bye bye.